Ever wondered how an airplane stays in the sky? Well, the answer lies in the fascinating world of aerodynamics. At the heart of flight, aerodynamics is a fundamental concept in aeronautical engineering, applying classical theories of fluid mechanics to external flows or flows around bodies. Now, when we think of aerodynamics, the first thing that often comes to mind is the flow around wings. Why so? Because the wing is the most integral part of an airplane. Without it, there would be no lift, and without lift, there would be no aircraft. But it's not as simple as it sounds. The aeronautical engineer's task isn't just to make the wing work. They need to shape the wing for the optimum combination of lift and drag, and understand how the vehicle's aerodynamics interacts with other aspects of its design and performance. So we understand that the wing's role is critical in keeping the airplane aloft. But how does a wing do that? Let's dive in. Imagine slicing a wing parallel to the center line of the aircraft fuselage. What you see is the airfoil section. This two-dimensional cut, or the airfoil section, is a critical component in understanding aerodynamics. The airfoil section has a distinct shape, crafted meticulously for optimum aerodynamic performance. One of the key characteristics of this shape is the chord line. Think of it as an imaginary straight line that spans from the leading edge to the trailing edge of the airfoil section. The length of this line is what we call the chord. Its length is not just a random measurement. It's a vital parameter in aerodynamic calculations and designs. There's another term that you should keep in mind when dealing with airfoil sections, the camber line. This line is drawn halfway between the upper and lower surfaces of the airfoil section, making it a median of sorts. Now, you might be wondering, why does this line matter? Well, the distance between the camber line and the chord line at its maximum point is referred to as the airfoil's camber. This is usually expressed as a percentage of the chord, and it's not just any random number. For most airfoils, the maximum camber ranges from 0 to 5%, and the point of maximum camber is typically located between 25 and 50% of the chord from the leading edge of the airfoil. These parameters, the amount of airfoil camber and the location of the point of maximum camber, are not just numbers. They are critical factors that define the shape of an airfoil and help predict its performance. The shape of an airfoil and its camber are crucial in predicting its performance. Remember this, every detail in an airfoil section, every curve and line, is designed with precision for a specific purpose. That purpose is to achieve the perfect balance of lift, drag, and pitching moment to ensure that the aircraft performs at its best for its intended mission. So, how does the airfoil camber affect the aircraft's performance? Let's dive into that. The amount and location of airfoil camber are two crucial numbers that help define an airfoil's shape and predict its performance. The airfoil camber is essentially the curve of the wing's cross-section, which significantly influences how air flows over the wing and, consequently, the lift and drag experienced by the aircraft. The maximum camber is the greatest distance between the camber line, a line drawn halfway between the airfoil section's upper and lower surfaces, and the chord line, a straight line drawn from the airfoil section leading edge to its trailing edge. It's usually represented as a percentage of the chord, the length of the chord line. For most airfoils, the maximum camber falls within the range of 0 to 5%. This might seem like a small figure, but even minor alterations in this number can have significant effects on an aircraft's performance. A larger camber can increase lift, but also increase drag, which could lead to a less efficient flight. Conversely, a smaller camber may reduce drag, but also decrease lift, possibly compromising the aircraft's ability to take off or maintain altitude. The location of the point of maximum camber is another critical aspect. It's typically found between 25 and 50% of the chord from the airfoil leading edge. The precise positioning of this point can affect the aircraft's stability. If the point of maximum camber is closer to the leading edge, the aircraft may experience higher lift at lower speeds. However, this could also make the aircraft less stable and harder to control. So it's a bit of a balancing act. Engineers must consider the mission of the aircraft and find the optimum combination of lift, drag, and pitching moment. This requires a deep understanding of aerodynamics and careful consideration of the airfoil's camber. Finding the right balance in airfoil design is key to optimizing an aircraft's performance. Another important factor in aircraft design is the wing planform. It's a term that refers to the shape of the aircraft's wing when viewed from above, and it's a key consideration in the aerodynamic efficiency of an aircraft. The wing planform is defined by several parameters, such as the span, the root chord, the tip chord, and the sweep angle. The span is the distance from one wingtip to the other. The root chord is the width of the wing where it attaches to the fuselage, and the tip chord is the width at the wingtip. The sweep angle is the angle between a line perpendicular to the aircraft's longitudinal axis and the line of the chord. It might be tempting to think of a wing as a flat, two-dimensional shape, but in reality, a wing's geometry is a complex, three-dimensional construct. This is where the concept of planform area comes into play. The planform area is not the actual surface area of the wing, but rather the projected area, or the area of the wing's shadow, if you will. This measurement is significant because it directly impacts the amount of lift generated by the wing. Different wing planforms yield different aerodynamic characteristics. For instance, a rectangular wing, where the chord is the same along the entire span, is simple to manufacture and offers good low-speed performance. On the other hand, a tapered wing, where the chord decreases from root to tip, provides better high-speed performance and is more structurally efficient. Let's not forget about the sweep angle. A larger sweep angle reduces the drag at high speeds, making it a common feature in supersonic aircraft designs. However, it also reduces the lift at low speeds and can lead to stability issues. As you can see, the wing planform is not just about aesthetics. It's a carefully crafted aspect of aircraft design, balancing various performance requirements, structural considerations, and manufacturing constraints. The shape of the wing, as seen from above, plays a significant role in the aircraft's aerodynamics. So, next time you're looking at an airplane, take a moment to appreciate the complex geometry of its wings and the thought that went into designing it. Aerodynamics isn't just about keeping aircraft in the sky. It's a fundamental concept that permeates through various aspects of aerospace engineering. Let's take jet propulsion as an example. Here, aerodynamics plays a crucial role in determining the efficiency and performance of jet engines. The design of the engine's intake, combustion chamber, and exhaust nozzle relies heavily on the principles of fluid mechanics to ensure optimal airflow. Moving beyond the atmosphere, the principles of aerodynamics help us in designing rockets and understanding their propulsion. From the shape of the rocket body to the design of its nozzles, every decision is influenced by how it will interact with the air around it, especially during the critical launch and re-entry phases. But the influence of aerodynamics isn't confined to just making things fly. It's also instrumental in making the aerospace industry more environmentally friendly. For instance, the aerodynamic design of an aircraft significantly influences its fuel efficiency. More aerodynamic aircraft require less thrust, and hence consume less fuel. This not only leads to cost savings, but also reduces the carbon footprint of each flight, contributing to a more sustainable future. Moreover, the lessons learned from aerodynamics have found applications in other fields as well. From designing more efficient wind turbines to improving the fuel efficiency of road vehicles, the principles of aerodynamics are helping us create a more sustainable world. Aerodynamics, therefore, is an essential puzzle piece in the complex world of aeronautical engineering. So, how does an airplane stay in the sky? It's all about aerodynamics. We've delved into the intricacies of airfoil sections, understanding how these two-dimensional slices of wings with their chord and camber lines play a pivotal role in the lift and drag of an aircraft. We've also explored the importance of airfoil camber, a key player in shaping an airfoil and predicting its performance. With a maximum camber usually within 0 to 5%, and its location falling between 25 and 50% from the airfoil's leading edge, these numbers are vital in defining the airfoil's shape. Moreover, we've discussed the wing planform, the bird's eye view of the wing, which is not the actual surface area of the wing, but its projected area, or the area of the wing's shadow. It's another crucial aspect that defines the efficiency and performance of an aircraft. Aerodynamics is not just about keeping planes in the air. It's a fundamental concept that influences the design of efficient, capable, and competitive aircraft, making them more environmentally friendly. It intertwines with other aspects of aerospace engineering, from airplane and helicopter aerodynamics to jet and rocket propulsion, and even properties of the space environment. Next time you look up at a plane soaring in the sky, you'll know a little more about how it stays up there.